You're live. Okay. So I'm Brian Wawok, and I'm a developer at DataStax, which is the commercial company behind Cassandra. So, quick agenda today. I'm going to introduce who I am. I'm going to tell you what NoSQL is. Then we're going to kind of deep dive in Cassandra. We're going to talk about how it works inside. We're going to do a little demo of what Cassandra does, and then we're going to talk about what is DataStax separate from the open source Cassandra. Okay. So, about me, I'm Brian Wawok. I'm developer, entrepreneur, grew up in LaPorte, went to IUSB here, lived in Chicago for a while, now I'm back in Mishawaka. Spent my time in Chicago doing finance, and then more recently I've been working remote for DataStax. I primarily do Java, but I do a little bit of Scala, Python, other stuff. Haven't been at DataStax a long time, so I'm not an expert in databases or Cassandra, but hopefully I can still provide you guys some value tonight. Okay, so let's just do one quick survey before we start. Who has used, group number one, who has used some form of NoSQL database before? We have 4.5. Who has used a relational database before? Probably 90%, and then who has no clue what a database is? Nobody, so we have some no voters. Okay, so this is good. I'm hoping to kind of target this top 4, number 2. You know where a relational database is, but maybe you don't know a lot about what NoSQL is. I'm hoping that for the number 1 people that have used NoSQL, they can still get something out of this. Maybe they can learn something new about Cassandra or just about a different NoSQL database. So, real quick, what's a big data system? 3 V's are volume, velocity, and variety. Basically, systems that involve lots of data, data that's moving fast, and data that may be changing. So these are all kind of candidates for looking at NoSQL. You just need to, what is NoSQL? So have you guys heard of the website ddengines.com? It's kind of, if you guys have heard of the TOB index, which is kind of like a popularity graph of what's the coolest language, what language do people Google the most. This is kind of that for databases. So it's not really that scientific. It doesn't mean which database is the best, but it kind of shows, you know, what databases are people working in, what are people talking about. And here I grabbed a screen cap today of the top 11. And you see 7 of them under database model. They say relational DBMS. So those are considered SQL databases. And those are Oracle, MySQL, Microsoft SQL, PostgreSQL, DB2, Microsoft Access, and SQLite. So those are a relational database or a SQL database. And basically a NoSQL database is everything else. So NoSQL databases are very different. They can do different things. We have MongoDB, which is listed here as a document store. We have Cassandra, which is the main topic tonight, which is a wide column store. We have Redis, which is a key value store. And we have Elasticsearch, which is a search engine. Any questions about this? Are you guys all?
What's the difference between a document store and a wide column store?
Yep, so document store is meant to store basically freeform JSON. So you have a bunch of data, every single row is going to be different. You can throw it all in, and you can do searches against all the data. Wide store is going to be, wide column store is what we're going to talk about tonight with Cassandra, which you see is kind of, you can have unstructured data in it, but it's a very, you kind of have a different end goal than you do with the document store.
Cool.
Anything else? I see puzzle books. Nope. Okay. So, first thing to understand when talking about distributed databases is CAP theorem. So it says there are 3 kind of goals that you can get in a distributed database: consistency, availability, and partition tolerance. And the classic thing is pick any 2. Realistically, everything's kind of on a spectrum. It's not that you get 100% of 2 and 0% of another, but when you're designing a distributed system, you kind of move around this depending what your goals are. So consistency is saying everybody in this distributed database, they see the same exact thing at the same time. So if you have 100 different people looking at your database, you all are going to see the same exact, you're going to see an update at the same time. Availability says if half our servers crash, can our client still fully use the database? Or does, when half the servers crash, does the website go down and you can't use the database anymore? And then partition tolerance is kind of the most strange one of these, but it's basically saying, can your database handle random parts of the network going down? So for example, if you had a two database system, maybe they both keep access to the internet, but maybe the network between the two databases goes down and creates a network partition. Is your database able to handle that? So let's look at some examples of this. So a simple database is something like Redis. Redis is generally run on just a single server, and it's just kind of a key value store. So you put data in with a key and a value, and later you can get it out. So think you have a single server running a single program. Is it consistent? Would everybody see the same data at the same time? I see mostly yeses. Okay. And then is it available? So if this server crashes, can people still access the data? See no's. So yes, Redis is not available, but it's consistent. And is it partition tolerant? Do you have to worry about losing a network connection in between a single machine? It doesn't really make sense because it's just a single machine. So we say Redis is partition tolerant. So databases like this, such as Redis, MongoDB, BerkeleyDB, Bigtable, HBase, we say those are on the bottom of the triangle. They're consistent and they're partition tolerant. And they're kind of color-coded based on the type of database. There's lots more. Pretty much any database in a single instance is gonna fall on this side of the spectrum. So then, next thing to think about is what if you have something like a MySQL or a Postgres master-slave setup. So you have a master database, everybody uses that master database, and then you have a slave database listening to the master, streaming in the changes. If anything happens to the master, the secondary database takes over. So let's just start with the easy one. Is the system available? Can it handle half the system's crashing? Yes, because the master crashes, the slave will take over. The slave crashes, nobody cares. So MySQL in a master slave is available. And then we say, is it consistent? Does everybody see the same thing at the same time? And as long as everybody reads from the master, it's consistent. You could choose to have people read from the slave and you're a little bit behind, so then you would not be consistent. But there's nothing that stops you from everybody reading from the master always being consistent. But partition tolerance, what happens if the network cable between the two databases gets cut, but nothing else happens? So people are updating the master and the slave's not getting the changes. Then there's a failover event. What would happen? You would lose all the data that happened from when the partition happened and when the master crashed. Right? So we would say a MySQL master slave is not partition tolerant. So these kind of databases we put on the left side of the triangle. We say it's consistent and available, but they're not very partition tolerant. And the third school of databases are what Cassandra is and what we're going to talk about today. They focus on they are available, they're always up, they're very hard to crash, and they're partition tolerant. They're designed for the network to be breaking and fixing itself constantly and not losing data, not causing anything bad to happen. But they give up a little bit of consistency. They say if two people read two different nodes in this cluster, you could see slightly different data. And it's the term that's generally eventually consistent, saying eventually everyone will see the same data. And it sounds worse than it is. Netflix has 1,000 node cluster or whatever, and their average consistency time is like 2 milliseconds. So within 2 milliseconds, everybody sees everything. So it's not saying like next week sometime you'll get the updates to your account balance. Like, you'll get it, it's just maybe not quite instantaneous. You have to be aware of it.
Facebook uses something in that range, right? Because one time I was with a friend and he saw one thing on Facebook and I saw an entirely different thing. Like after he like updated his profile picture or something.
Yep. So yeah, we'll talk a little bit about Facebook, but yeah, that's anything like that. So anything like, say you're just streaming like sports scores from a website or something, that can be eventually consistent because if you're 2 milliseconds behind what actually happens, you're not going to know the difference, right? But if your bank is eventually consistent and every time you reload the page, your bank balance changes, that might be a problem. So it's kind of, you have to look at what you're doing and what it matters. And, you know, like I said, different databases, you can do different things that kind of shift this around. So like Cassandra has something called a lightweight transaction where you say, I have this bunch of stuff, I want it to all happen at the same time. And that actually would behave like it's at the bottom of the triangle. It's consistent and it's partition tolerant, but it does not have availability. So it does not, if you have even one node down, that transaction cannot complete. So, right, things move between these, but this is kind of like their general behavior. Any other more questions? Okay, so this is CAP. And the question is, why not use a relational database? And what does a relational database give you? It gives you normalized table schema, so it's a way to have data in your database that you don't have to repeat over and over again. If you have a table that called states, you can list all the states, and you only have to list it once. It allows you to do joins, which are really handy for reports, really handy for kind of getting overview of what's going on. And they have the concept of ACID, which is kind of atomicity. Let's see, I think it's good to see.
Add grade insertability.
Kind of, right? It's kind of like that, but the idea is ACID only applies to a single instance. So the D is durability, for example. It's when you restart the database, is your data still there? And like that's cool, but that's only, you can only think about a single system like that. You can't think of a whole distributed system as being ACID or not. So it's kind of, it's cool for relational databases, but it doesn't scale. So the cost of this is you want to do really big join. You have 1 billion rows and you need to join with another 1 billion rows. You either need enough memory to hold all those keys, you need something. It's very hard to do giant joins. And then you have sharding. So I'll talk about that in the next slide. And the pitch is people need their databases to be fast. They need them to be always on. We want to just run our databases on normal commodity servers. We don't want to buy a $6 million super race car server for a database. And how often do we actually need transactions? Most data in the world, like how much, every website you go to, every movie you watch on Netflix, most things don't actually need to be transactional. So forcing yourself into a relational database is limiting your data size, limiting your data speed, but it's not actually helping you that much. So a single database limitation. So I went to AWS today and saw what is your instance type with the most memory. So they have an R3 8 extra large. It has 244 gigabytes of memory. So if you need really, really fast data and you want to fit it in one database, you can have 244 gigabytes of data. That's kind of your limit. And really there's going to be some indexes, some overheads, but right, that's your limit. If you're okay with not everything being in memory, you can do, okay, I'm going to run a MySQL instance. I want enough memory so my indexes are in memory, but the data can be in disk. So rough guess is maybe 10% of your data size will be an index. So that says you can fit 2 terabytes of data on your database with a 200 gigabytes per index and still be reasonably fast. But if you have more than that, if you have, you want to have 400 gigabytes of memory,
your database, what do you do? Like, how do you get, this is the biggest size AWS sells. And the answer a lot of people do is what's called sharding. It's, okay, I'm going to have two, sharding with a D, note. I'm going to have 2 instances or 4 instances of my database, and I'm going to store 1/4 of my data in each of these 4 databases. So it's okay, like it works, but then you have to, in your code, you always have to manage, okay, which users in which database, go to the correct database, pull your data. You can no longer do joins between different parts of the shards. You can no longer, reason about them as simply because there's not you can't do a transaction across shards. You kind of start to lose a lot of the relational magic when you get beyond this data size. So it's the time to start thinking about, okay, maybe relational isn't the right fit for this data is this size. So say a couple 100 gigabytes of data that needs to be in memory, or a couple terabytes of data that can be in disk. So once you start approaching that, you might need to do something NoSQL. Yeah, so that's where Cassandra comes in. So I'm going to do history of Cassandra. There was a paper by Google in 2006 called Big Table, and it talked about, here's how we store billions of rows of data to do our search engine. Didn't really have code, I don't think. It was just kind of like describing, this is how we store a bunch of data. Then in 2007, Amazon had a paper about dynamos that says, this is how we distribute a cluster of machines to serve up metadata. I believe it was used to serve up the metadata around Amazon S3, which is their file storage system. And again, I don't think there was any code. It was just kind of saying, okay, we do a cluster of machines this way. We call each machine a dynamo, and this is kind of the way the machines cluster together, and they self-heal, and they do all this cool stuff. So the guy who invented the dynamo at Amazon, he went to Facebook in 2008, and he kind of said, I'm going to take these 2 things, and I'm going to tie them together. I'm going to store my data on each machine, like Google says for Big Table, but I'm going to connect all the machines together, like I did in my last job at Amazon with these dynamos. So he did this. He released it as an open source project in Google Code in 2008, and Facebook used it at this time for, I think, searching private messages or inbox. So you could, if you, 2008, 2009, did searches on your inbox on Facebook, you were using the early version of Cassandra. Once it became open source, some people took it over, started rapidly releasing new versions. 3.0, Cassandra 3.0 just came out in November. Yeah, and now it's backed by commercial company DataStax. So we have open source project Cassandra has everything that I'm going to talk about today, and then there's a commercial company DataStax who's paying for the development, and that has some things they can sell you to add value on top of Cassandra. Any questions about this? Nope. Okay. So let's think about how do we manage big data. So we have more than a couple 100 gigabytes of data or a couple of terabytes. What can we do to manage it? We distribute data across nodes. The more servers we can put our data on, the more data we can have. And as I said earlier, we can relax consistency. Being less picky about when every single node knows about a change lets you be a lot more scalable. Another option is to kind of relax schema requirements. Don't force people to, ahead of time, define exactly what the data is going to look like. Some data is going to change as it goes. Don't force that. And optimize data receiving. So it's saying, think about how you're going to read your data as you're writing it. Don't just write all your data to a database and then sit down and come up with queries to read it back. Kind of flip that around and say, I'm going to have some data. What do I need to get out of it? Once you know what you need to get out of it, then you know what you need to write to get there. So it's kind of, you think about it backwards from a relational database. So Cassandra, this is what they try to do. The idea is you have a cluster of nodes, and you can have many different clusters in different data centers, and they will all communicate. So we'll talk more about this as we go. Cassandra is a massively linear scalable database, so it's fully distributed. There's no single point of failure. There's no concept of like a master node or a primary node. All nodes are equal. If you want to add more nodes, you just boot up 10 more servers, join into your cluster. Now your cluster is bigger. You need to do maintenance, you just shut down a node. And it really does, scale. Like this is kind of like, maybe it just sounds trite that it scales linearly, but it really does. If you do a test against 10 nodes and 100 nodes and 1,000 nodes, which is something that we do, you can really see your performance really does go up by 10 and by 100. You really aren't limited. And you can Google benchmarks. There's lots of different benchmarks of different databases. Some do better than others. Yep. And then this is going back to how is it architected? How is it architected? There's a cluster layer inspired by the DynamoDB, and it's completely masterless. So if a client wants to do a query, you just connect to any node in the system, send it your query. That node will do all the work to gather the results, and then it'll package them up and send them back to the client. So that's kind of based on the Dynamo system from Amazon. And the data store within each system is kind of based on the Google Big Table thing, where we have wide columns. And I'll get more into what wide columns are, but it's kind of the way each node is structured. Does this level make sense? Like the way that we're splitting up the two, the way individual node is structured versus the way the whole cluster is structured? Without really knowing the details yet, because we'll get into the details.
So when you say you're gonna hit a node, do you actually choose a node, or do you like hit a load balancer or something? And how does the
You
node
have no
get
load
chosen?
balancer, so
How does the node get
you're
chosen?
allowed to query any node.
Okay.
So you could just hard code your favorite node. Just say that the server sends all his queries to his favorite node. What really happens though is the data is going to live in different nodes, because not all data is going to be on all nodes. So the driver on your server is actually smart, and he knows what server which data lives on. So he kind of helps the process along by he starts a connection and queries to somebody that's going to have his data, and he like keeps track of performance data. How long does each node take to respond? And he finds kind of the best node. So they kind of like self-select. Okay, this piece of data is on these 4 nodes. He's gonna like kind of split up his queries and find out, okay, this node is the closest one to me. And he may know that based on a properties file that says he's in the same data center, or he may just know that from latency and how long it takes. So then he will start using the closer nodes.
Okay.
So you don't have to do that. That's just like an optimization. You can query the wrong node, and the wrong node will go out to the right node, get your data, and bring it back. But obviously, doing 2 hops is going to be slower than just talking to one node. Anyone else? Okay. So we're just going to do kind of a couple of examples. Let's go through these real quick. For example, Spotify, they have, I think the base of this slide presentation is like 2 years old, so I'm sure they have more now, but they had over 50 terabytes of data that had to do with playlists, who's following what artists, what the radio stations are, all that stuff. So again, if we said that a database can hold maybe 2 terabytes of data, if they had 50 terabytes of data, they would have needed 25 databases, 25 backup databases, and then the magic to manage all that. So with Cassandra, they're able to just have a single cluster, put everything on it, and have success. So eBay has a recommendation engine. It's basically every time you go to eBay, every auction you click on, every link you follow, they save all of that to your Cassandra database, and they use it for real-time predictions. So there'll be kind of advertisements like, hey, how about this? It knows you clicked on a bunch of baby shoes. How about these baby socks to go with your baby shoes? So they need something that handles huge amounts of data, so at least 250 terabytes of data, and could give you the results in real time. There's lots of ways to store 250 terabytes of data, but there's not a lot of ways to do a query in, you know, a tenth of a second that's going to tell you something useful. And if you look up eBay, they've published kind of a bunch of papers about Cassandra. They were kind of doing it 2013, 14. So it's a couple years old. It's not always up to date with the newest, but they did. I think they probably have the most papers of anyone just kind of saying, how do we model data at eBay, and how did we come to this? And it's kind of, if you're having trouble thinking of how to model data, looking at some of these eBay papers is a pretty good resource. Another big client would be Instagram. So they originally used Redis, and Redis is just kind of an in-memory key value store. Everything was in Redis, everything was in memory, everything was fast. But what happened is, as they got more and more and more clients, they had to add more and more and more Redis instances. So they got to the point where, you know, they had 300 servers just so they have enough memory to hold all their data. And realistically, they didn't need all their data in memory. If somebody hasn't logged into Instagram for 6 months, why are they paying every single day to keep that data in memory? So by switching to Cassandra, they were able to say, okay, we're going to keep the popular data in memory, but most stuff can go to disk. So they published a story, a big success story, and saying we were able to turn off 75% of our servers because we just didn't need to keep everything in memory anymore. These guys, I don't know a lot about these guys. I think they use Cassandra for fraud detection. These guys use it for the Internet of Things. It's just, in general, places that have sensors, and, you know, if Uber wants to make a fleet of self-driving cars and then collect, you know, data about each car each second, and they have thousands and thousands of cars, at some point they need something to store all that data. So any big system like that, it's nice to have a distributed database, or it's necessary. Okay. Those are kind of like sample use cases. Now we're going to talk about a little bit about like how Cassandra actually works. How does it do the magic? So, what is a cluster? It's a peer-to-peer set of nodes. A node is a single instance. So in AWS or something, it'd be a virtual machine. Could be a physical server. It doesn't have to be. Most in any virtualized environment, usually you're just going to be a portion of the server. A rack is kind of a set of nodes that are close together, and that's useful because for your data to be durable, we don't want all your data sitting on the same rack. We want your data spread out. So from a rack perspective, we want to spread our data between many racks. But from a latency perspective, we want to stay within the same rack. So if a client needs data and it's on the same rack, he's going to ask that guy first. The data center is kind of a set of racks, and then clusters the whole thing. So if you're on Amazon, a rack is a availability zone. So everybody in US East 1A, that's one rack. If you're in US East 1B, that's another rack. A data center in AWS is US East. It's a collection of availability centers. And then clusters, all your nodes connected together, however you connect them. Does that make sense? Okay. So, nodes join a cluster based on a configuration file. You basically, to run Cassandra, you have a single configuration file called cassandra.yaml. Has a bunch of settings in there. One with the cluster name. It says, what's the name of my cluster? Just to make sure you don't accidentally join somebody else's cluster. And there's security stuff, but that's kind of aside. And then you have a seed node, which is a set of IPs that you use to when you first get in a cluster. So normally you'd put at least one seed node in each data center. And to add a new node to the cluster, all you have to do is know that one of those seeds somewhere is up and you can reach them. Once you reach one of those seed nodes, he's able to tell you about every other node in the cluster. So the gossip-based system, all the nodes, will learn about all the other nodes. But the seed node is just kind of like the starting point. So just have a couple seed nodes, spread them out. It's not an exact science. If you have 3 or 10, it doesn't really matter. But you don't want to put every single node as a seed node, because then it can take longer to start it up and it gets complicated. Yep, and so here's graphics. So a new node is coming to this cluster, node 4. He says, I want to join the cluster. He has in his config file, hey, node 1 has this IP, 127.0.0.1. So he goes, hey, I want to join the cluster. The node says, okay, and then he tells you about the rest of the cluster, and he tells the rest of the cluster about you. So that way, every machine eventually learns about every other machine in the cluster, every other node. Again, the coordinator is the node who's answering your query. So when a client makes a query, he can pick any node in the cluster, but he's usually smart and will usually try to pick a close node or a fast node or a node that has the right data, maybe all of those. But the nice thing is, the client, the driver, is able to change this on every single request. If he's in the middle of the request and the coordinator goes down, he will pick a new node, try the request again. To your application, it's totally transparent that a node just exploded. Like the client does not even notice downtime. He is reading from the cluster. And the coordinator applies what's called the consistency level. So one thing interesting is every single time you read to the cluster, or every time you read from the cluster or write to the cluster, you pick a consistency level. And it says, how many nodes have to agree with this? So you can say consistency level 1 that says, ask the first node a question, whatever his answer is, I'm going to take it. The other extreme is ask all the nodes my question. The cause of all this is because we have eventual consistency. At any given time, different nodes are going to have different views of the data. By saying I'm going to ask all the nodes the data, you're guaranteeing that you get the most current value. So I guess examples are if you're a web page and you're showing some sports scores to somebody on a site, it doesn't matter if your data is 1 second old. You would just read it with a consistency of 1 and say, just pick some data. It's going to be pretty close, and just show it to the user. But the flip side is maybe you're doing a write and you're doing a password update. You don't want their password update to only go to one node and then the rest of the nodes don't get it. Like password updates is very important. You want to make sure everybody has that. So you could do a write with a consistency of all. That says go to every single node that holds my data, tell them all about this change. And then somewhere in between those two is, between 1 and all is quorum, which is basically 1 more than half. So if you have 3 nodes have your data, you can do a quorum of 2. That's generally the best balance between performance and consistency. If 2 of the 3 nodes acknowledge that you write something, and then if somebody else reads and asks 2 of the 3 nodes, you're guaranteed to get the newest data, right? Because if nodes 1 and 2 got the write from node 4, and then you did a read at quorum, your read could go to 1 and 2, you'd get the new data of both. Or 1 and 3, you'd see the old data and the new data. You know the node 1 data is newer, so you would take that. Or 2 and 3, again, you would get old and new data, but you know which one's newer. Any questions here?
What's any?
Any, I think, I need to look into it. I don't use any. I have a table coming up, it might be I think it's more like 1 though. I think it's just somebody needs to tell me it. I don't know. Okay, so let's talk about partitioners. So we have data, we have a cluster of nodes. One thing we have to do is each data needs to decide where it's going to live. So you write some data. In this case, we've made a users table. We're saying we're going to insert into users first name of Oscar, last name of Orange, and a level of 42. You go to the partitioner, and he's going to say which nodes are in charge of this data. Because basically, there has to be a deterministic way to always know which node a given set of data is. If you didn't have that, you would always have to go to every single node in the cluster and ask them, do you have my data? Do you have my data? So partition is the way you deterministically assign data to some set of nodes. I think we'll talk a little more about that, but it's just every data has nodes that it lives on. So, replication. A replication factor says for each piece of data, how many nodes should it live on? So you can choose replication factor of 1, which would say each piece of data only lives on one node. If it crashes, my data's gone. I can never get it back. You can do replication factor of 10 that says every data lives on at least 10 different servers, which your data is going to be very safe, but it's going to be very expensive because if each server only holds 2 terabytes of data, and you would need 10 servers for each 2 terabytes of data because you're replicating that data 10 times. So usually you balance the safety of the data versus how much money you want to spend on storage. Very, very common replication factor is 3. I think a lot of people talk about using 3 copies of things. You keep 1 copy close, 1 copy far away. Kind of the odds of 3 independent servers exploding at the same time should be fairly low. And then the layer on top of that is kind of your replication strategy. How do I divide this data up, other than just how many copies? So you can say, if you only have 1 data center, then it's pretty simple. It just kind of randomly picks some nodes. But if you have, say you have a European data center and an American data center, you might say, I want at least 1 copy in Europe, and I want at least 3 copies in America. So you can decide where in each data center you want your data to live. And again, that is also kind of a function like replication factor of how much do you want to spend, how much redundancy do you want, but then also a function of speed. If you force data to be in every data center, that's going to make your client that you have in Europe, if he can query the European data center and get the data without having to go all the way to the American data center, it's going to be much faster. So it's, again, kind of like building up groups of these clusters. Again, there's no concept of masters, there's no concept of replicas. It's just a matter of, if your replication factor is 3, there's going to be 3 nodes that have your data. There's no authoritative source, none's any better than any other one. And clients are just going to pick the one that's closer if they can. So yeah, so replication factor of 3 is kind of like a good place to start. And you do pick this on a per key space factor, so you could have some key spaces that are very important, like maybe you have password data and you could put the replication factor of 5 or 6 because you really want to make sure you don't lose everybody's email address. And it's a very small table, so you don't care. But then maybe you have this web data that's, analytics data that's huge, and you could never afford 5 copies of it, so you just put a replication factor of 3. So you kind of pick for each set of data how much replication you need. And again, if you're not being simple, you're in the...
I have a question.
Yep.
So at what point are you picking that strategy? Is it determined by the type of data that you're writing to the system, or are you doing that as you're doing the writing? And when is that?
So a key space or the schema is kind of like where you create your objects. When you create that key space or schema, you set the replication factor, and you set the strategy. So you set those when you create that. But then when I talked before about quorum or the consistency, you do that as you read or write the data. So that is more flexible, it can change over time. This stuff, you want to kind of think about more ahead of time, and it can be changed, but it's potentially more complicated to change down the road. So you want to try to get this part right.
If you're establishing your
Yeah, when you're just kind of designing the whole system, try to get this part right. And again, as you add new data centers, you can change it. So this example says we're going to do a network topology strategy, and it says our data center on the East Coast, we want 2 copies of the data, and DC on the West Coast, we want 3 copies of the data. So we're going to have a total of 5 copies. And you can keep adding data centers. You can have, some people have as many as 10 or so data centers. Each data center is going to have different needs. Some might be like a disaster data center. You can just have 1 copy, let you run far fewer servers, etc. So you just kind of play with this based on what your requirements are. So, hinted handoffs are something that you have to deal with in a distributed system like this, and it basically says sometimes when you want to write data to a node, say you have a replication factor of 3, one of those nodes could be down. It could be server could have failed, it could be getting rebooted for system maintenance. So you can't always write to all your nodes when you want to. So what we do is we have a kind of a hint table where we say, okay, when I see this node again, when it comes back alive, I need to tell them about some stuff. So later on, the node comes online. Yeah, so in this case, the node at the bottom died, even though you wanted to write to it. But because, say, your consistency level is only 1, you didn't have to write to it to be successful. So your write still succeeded, even though he was dead. And then later on, a couple minutes later, he comes back, then you tell him about it. So it's just one of those interesting things in distributed systems. You can't rely on 100% of the nodes being up 100% of the time. If you had a 1,000 node cluster and you could only do anything if every single node was up, you would have very, very high downtime. Because the odds are that something's always going to be broken, right? So as you would add more nodes, you would have less and less uptime. So hinted handoffs, things like this are one of the ways that you deal with. Nodes are coming up and down all the time. Doesn't matter. You have many copies of the data. You're good. Yep.
How does this work when say node 4 also goes down as soon as it puts it in the hint table, and then it wipes the hint table?
So the good thing
is it backed up?
The hint table is internally another distributed table. So again, he would make it to say 3 nodes. Yep. And system tables are something that you may want to have a higher replication factor. You might want more copies of them. But
Is the table kind of like a traditional SQL table, as much as there's
yes, so
columns and rows?
you have rows, you don't really have columns. That's why it's called a wide column. So we'll get that in the data modeling. But think of you have a primary key and you have a bunch of stuff. And a table is made up of a bunch of those.
Let's say you have something kind of familiar with on a part next year, where you have part number and description.
Yep.
And that's on 3 nodes.
Yep.
And you got manufacturing in Germany and in St. Joe. And someone realizes the description is wrong. They pick apart.
Yep.
So they both, within seconds of each other, goes ahead and makes an update to the description to the node that's closest to them.
Yep. And they both.
Both one are different. Now, which one wins?
So first question is, what consistency level do they have?
That's my question.
Yeah,
What
so-
do they have?
Okay, so question is, we have 2 different data centers, 2 different people both writing to the same thing, and they both want to make an update. You have American guy and you have German guy, both updating the same data. Who wins? If they did a write with consistency of all or a quorum, it would have gone out to, the first write would have gone out to most of the nodes, been saved, and then the second write would go out to most of the nodes, be saved, and the second write would win. If they had consistency of 1, they would each go to 1 node, be returned success, and then they would both kind of spread that data around the cluster. And then what ends up happening is, and kind of the key to the whole thing is that it looks at the timestamps. Whoever has the newer timestamps, the winner. So kind of,
Last one wins.
yep, last one in wins, which is kind of naively what you'd expect. And kind of, what really wins anyway. Like if you think of, if you have 2 people clicking the button at the same time, somebody really clicked first, but you don't really know. So it's kind of a toss-up at that point. But yeah, that's why clock syncing is very important. You need something like NTP, you want to have your clocks right. If you have a server with runaway time and it's 6 hours ahead, people are going to get weird things where they enter something and then 4 hours later you update, but it's still coming in as an old update and bad time. So clock syncing is important. It doesn't need to be perfect, but if it's there within a few seconds, then it would generally behave like you expect. The guy who did it last would eventually win. There's going to be a time in there where it's kind of inconsistent. Different clients can see different descriptions, but we're eventually consistent. Eventually, everybody's going to agree the second guy won. And the second guy's the guy with the higher timestamp.
In environment, I'm familiar with, if you want to have, and, let me think of my question here. If you want to have, that two people doing that at the same time, you would go ahead and try the second one. You do optimistic lock, and you would go ahead and you would check to see if the contents change at the time you do the post. So the contents change since the last time you read it, then that user back an error instead of that they can't update it because it's already.
Yeah, I mean,
where is that similar sort of thing available?
So if, again, that's why you have the concept of consistency on your writes. You can say this node's going out to everybody. And then there's also a concept of lightweight transactions that say, you know kind of the previous timestamp in this column, and you can say apply this update only if this is the current timestamp. So you can kind of get around and he'll check every single node, make sure everybody agrees this is the right timestamp, and then he'll apply it. But again, that's a very expensive operation. You don't want to do that if you can. You don't want to do that a million times a day, but maybe it's okay for changing passwords or this important stuff. Go ahead and do that. But if you're just doing click data, everybody that clicks on your website, you're saving that. Don't do these big locks and all this big crazy stuff, because then you lose the scaling, right? You lose the ability to just add more nodes and go faster. So you have to kind of weigh when you need that level and when you don't need it.
Even if there was parent-child relationships, like bill of materials, then NoSQL.
Yep, so different, I can't generically say for all NoSQL, because right there you handle it a little bit differently. But in Cassandra, like in this, you don't make relations most of the time. So, example of this is, I think eBay might have 4 or 5 different tables that deal with users in some way. It could be like your searches, it could be your clicks, it could be whatever. What you normally do is you replicate the user's email address and first name in every one of those tables. And then when they go in the preferences and they change their username, you have to go out to 5 tables and update them in other places. So it's kind of more convoluted process, but you denormalize your data. You say, it's more important that I can scale and that I'm fast, and if that means I have to store this dude's email address 5 times, you just do it, right? So it's a trade-off, right? It's harder to code, it's harder to work with and think about. Because now changing your email address, now you have to think of these 5 other tables that use it.
Data is only as accurate as
Yep. But sometimes it doesn't matter, so that's, yep.
So you were saying, going back to the question about trying to be consistent and whether or not you want to look at, for instance, a date stamp. So you can, if I wanted to, for instance, force the data that I was writing to look at a date stamp of the other information that I might be overwriting, I can do that when I do my write. If I
You can say only update this data if something else is still true, and then you'll get back that worked or didn't work.
Okay.
But realistically, in a distributed,
You very rarely do.
yeah. And realistically, you could say, yeah, that's fine, it works, and then some dude 1 millisecond later just clobbers what you just wrote with whatever he wants, because he doesn't care. So,
Yeah.
right, everybody would have to kind of agree on, everybody has to play nice. Okay, so consistency. I think we've kind of already talked about this. It has to do with when you write, how many nodes have to agree that your write was successful before you say yes? and a read is how many nodes are you going to check that the data is the same before you say yes. So it's, so again, in this case, node 4, he's doing a read, it looks like, to node 1. So it's consistency 1. Or if he says consistency 2, he's going to ask 2 nodes. So here's the table. So here's any. Write to any node and then store hinted handoff if all nodes are down. Okay, so any even works with a write if every single node is down. So it's something that you really don't care about. You just want to throw this at the database. Hopefully it will eventually make it to the database. But again, I've never used any, so it's not something that I think you normally do. I think the two most common ones I use are one or quorum, and then sometimes I would do, there's consistencies built on top of that. So there's local one, which says just give me the closest one in my data center, that's all I care about. And then there's each quorum, which says if I have 3 data centers and the quorum is 2, I would want every single data center to have 2 nodes agree. So each quorum is kind of like the way you start building up. I want every single data center to know about this change, not just my data center. So when you get a multi-data center setup, a lot of things that you normally would have done quorum, you instead will do each quorum, which again is more expensive. Maybe instead of talking to 2 nodes, you have to talk to 6 nodes or 8 nodes. You need to be careful. Do you really need every single data center to acknowledge that you just changed the product description? Maybe you do, and maybe you don't. Right? Everybody's going to get it eventually, but how many need to say yes before you can tell the client how successful? Then we have serial. You don't use those much. There's like, you can do 2, 3. There's even more than this. I think there's probably 25 now, but usually it's like all one quorum, each quorum. Usually those will cover most of your cases. Okay, so this is kind of saying, what's the difference between immediate consistency and eventual consistency? So immediate consistency is saying your read's always going to give you the most recent data. If you do a consistency level of all, you do guarantee this, but it has a cost. You have to go to every single node. As you add more nodes, it can even get more expensive. It is smart. It's not going to search the nodes that don't have your data. So if you have a replication factor of 3, it's only going to look at the 3 nodes that have your data, but all 3 of them will get checked. So it's not the worst thing in the world, but it is going to be more expensive than consistency of 1. And tuning consistency is just kind of the process of, maybe you start your system, you start doing most things with quorum, and then you kind of see how things go. Like maybe writes, you start to set some to 1. You kind of just can change them over time. There's no rule that your consistency for writes or reads needs to always be the same.
Right.
Yep. Yep.
For immediate consistency, is it true to say that it's only immediate from the time that the client has received back confirmation?
So if you do consistency level of all, when the server agrees that everybody has the data, he will start to send the client back an okay. That's kind of the starting point, right? If you did like a diagram. So by the time the client got back, your data was changed, somebody else could have already overridden you.
But if you had a huge, really distributed system, isn't it possible that while it's still waiting for the okays from everybody, that some people would tap more of that record and then get the new version or the old version?
Yeah, so
I mean, it's very fast.
yep, if they did a read of 1, they could get the old version or the new version. So let's step back. So let's say I'm going to do a write to all my nodes with a consistency of all. So I'm saying I want every single node to know about this. As that is propagating out, you could have clients reading with a consistency of 1. They could see the old version or the new version, depending on luck of the draw. But if they read with a consistency of all, they would check all nodes, they would see there's new data, and they would give you back the new data. So again, that's why your writes and your reads, they don't need to be the same consistency. Right? It's super hard to kind of think about, because you just need to kind of like sit down and look at all the cases. How perfect does this need to be? What happens if this data's stale? What happens if some people see it before other people? I don't know, but you find out doing this that most things don't need to be immediate consistent. The more and more you do it, you kind of see, adding this new song to this list that an artist has sung before. If some node sees the old version for 3 milliseconds, it probably doesn't matter, right? Somebody's going to reload the page and they see the new one. Most things, many things can be eventually consistent, and you're all good. And this is again saying, why is server clock important? Because that's how we know who wins. Again, it doesn't need to be perfect. It should be within, ideally maybe 100 milliseconds or something. If you use something like NTP, you can usually get close enough. If you do have clocks that get haywire, you kind of want checks for that, so maybe some server monitoring or something. The cluster itself is aware of that, and it should detect that this client is being haywire, but it's just not. Haywire clocks are not that good for this system. Yeah, so this is just saying Netflix and other stories is saying we use a consistency of 1 for everything, but we get pretty much everything gets consistent within a few milliseconds across 1,000 nodes. So it's how much are you going to worry about a few milliseconds? It matters for some things, and you have to be aware of it. You can't read the data, change it, and write it back. If you're like incrementing, like you have to be careful about stuff like that, right? If it's a bank account and you want to add $10, you probably don't want to read it back with a consistency of 1, add $10, write it back with a consistency of 1. It's probably not a good way to do a bank balance. But other things, that might be fine. Right? Comments in a blog, it might be okay just to read it once, write it once. Okay. Next up is, how am I on time? So it's 7:30. Another 15 minutes?
Yeah, that's probably good.
Okay. I'll fly through some of these. It just gossips just the way all the nodes talk to each other. Once per second, a node says hi to a couple other nodes, and through that, all the nodes learn about all the other nodes. You can see nodes. Each node has something called a snitch, which says, where am I? So it's some way to determine where you are. Like I said I guess here's a list of some of them. So like the EC2 multi-region snitch, he's going to look at your node and say, okay, you guys are in the same availability region, so I'm going to put you in the same rack, or whatever. And it's just going to kind of give your nodes a hint where everybody else is. The nodes will do kind of some internal testing of their own, and they keep track of how fast other nodes are, so they know who's close and who's far. But it gives them kind of good starting points to have a snitch set up. A concept of repair. What this says is, if a node is offline, it could miss some writes, and then it comes back online, it could kind of have some stale data. What you do to do that is you want to do a repair. So every so often you want to go to your data and say, do other people agree this is the newest value of this data? And the easiest way that this happens is there's something called a read repair chance. I think default is like 1%. So 1% of reads, even if you only ask for it on one node, if you really go out to 2 nodes, make sure the data is the same, and it just kind of like double checks that all your data is fresh, and it kind of deals with the fact that nodes are coming up and falling down. As an optimization, it doesn't read all the data twice. It actually just reads the data once. And the other node, it says, give me the hash of the data. It says, does the hash match this data I just read? And this actually applies to any time you do a higher consistency than one. You only read the data once to get the hash from the other guy. Speeds you up. Whether there's a tool, you can go command line and you can do it. I think you can do it like once a day or once a week or whatever, just to kind of ensure that there's no strange data. How do things, so that was all about reading. There's a section on writing. I really want to get to the demo, so maybe I won't do a lot about this, but it's basically relational database. You normally kind of update the data in place. Not always like Postgres doesn't, but something like that. Cassandra is just always just append the data, append the data, append the data, and then when you go to read, you look at all the things you've appended and figure out the answer. So you have a concept of a mem table, which is your data in memory. When a write comes in, it goes to memory, and it goes to the commit log. The commit log is like an on-disk backup. Once the mem table fills up, then you dump it out to an SS table, which I'll get to in a second. It's a file, and then every so often you combine those SS tables into new ones. So we had a question earlier about kind of what the internal structure of the data looks like. So this is what it is. You have a partition key which says where do I find this row, and then you have the row itself. And the row itself can be the same for every row. It can be different for every row. It's really just a blob of stuff that lives on a disk. And this one stuff reading basically just says when you read, you need to do the reverse of the write. You have to check, does the memory version of this table have data? Does the disk version have data? And kind of combine those up and figure out what the newest data is. Okay. And then there's the concept of compaction, which says, as, I guess Tombstone, let's talk about Tombstone a little bit. So Tombstone is when you delete data, you can't just nuke it out, you can't just erase it from disk, or any node that was down. When it comes up, it still has that old data, and so you'll be like, hey, I have this data, and he's going to spread it around the cluster, and the thing you deleted will come back. So Tombstone is you put a marker on a row that says undeleted. So then if a node comes back, says, hey, I have this data, you're like, no, you don't, here's the Tombstone, go delete it. And you kind of decide how long to keep those around. The default is for 10 days. So anything you delete sits around for 10 days, then eventually gets wiped out. You configure this per table, but it's kind of the fundamental reason why you don't want to use Cassandra for something that's going to be constantly updated. So like using Cassandra for a messaging queue where it's just like write a node, read a node, write a row, delete a node. Just doing that over and over again, you're going to end up with your data growing and growing and growing because you have all this data with tombstones. And eventually the server will say, this row has too many tombstones, it's going to take me too long to figure out what the current data is, I'm not reading it. I'm going to throw an error with it. That's a good one. Why we need them, does that make sense? Why we have to have tombstones, why we have to eventually delete them, or we never get disk space back for things that change. Cool. This is more about how it's stored in the file system. The main thing is rows are what we deal with. You have a partition key, which says how to find it, and you have data. And you can do different things with data. Sometimes there's some complex things like lists instead of map, but really it's just, you can also just store some JSON in a column, it doesn't really matter, it's a lot of stuff. I want to demo real quick. Very simple.
is it visible-ish? Okay, so there's a tool on GitHub called CCM called Cassandra Cluster Manager, and it's basically, it lets you on your local machine run a cluster. You just type a couple commands, you get a little cluster. You want to, it's not for like a production, but it's cool for demos, and it's cool for development, because as you change your code, you can deploy it immediately. So I just said, make a cluster, give it 3 servers, and then I want to start. Start. See what's going on. We can say CCM node 1 ring. We say, what's the cluster look like right now? We could say there's 1 node and he is out. So I screwed up and didn't have enough ports open. So I'm going to kill everything. It probably works. Again, Cassandra is designed to be durable, so it's if a node dies, you can start it right back up. It's not a big deal. If some data gets corrupted, it should fix itself. Okay, so that's good. Then I can say, what's the cluster look like right now? It says I have 3 nodes up, IP addresses of 1, 2, and 3. They're all in the same rack. They're all operating, and load is like how much data do they have? They just have a little bit of system data stuff. The next CQL-SH is kind of like the command line version that lets you access the cluster. There's a separate GUI tool, but very basic. You say I want to create a key space called test KS. Key space is like a database. It's like a collection of tables. And when you create the key space, this is where you say with replication equals, and you say the class of replication is simple strategy. I'm going to say the replication vector.
Which one was simple strategy again?
Simple is just assume you only have 1 data center.
Okay.
So there's no concept of multiple data centers, but you have the concept of racks and stuff. Well, very simple. I did that. Okay. And then I'm going to create a very simple table. I'm going to say create table of users. It's going to have a user ID, which is effectively UID. First name, and the text. So this is very similar to, a SQL. It's, it's, under the hood, it's not like SQL, but it's kind of trying to give you a view into things that look similar. I made a table. I can use describe users. And it says, okay, I made a table. It's got this user ID as a primary key. It's got an age, a first name, and a last name. Here's all this optional stuff. When you're making the table, you can change it. Here, this GC gray seconds is how long tombstones stick around for. This is my read repair chance, so it's actually 10%. Or is that 0.1%? I don't know, I'll have to look. Here's read repair, 0. So there's different settings. In general, everything's compressed because we just treat the column as a blob of stuff. There's no cost to us to compress the data, so generally all the data gets compressed. You can turn that off if you wanted to. So then I want to write some records to it. So insert into users. This is what it is like. Just like SQL. Maybe except that we need to do function, but good.
users, right? Smith, Smithers, Smithers. Just like SQL, you can go select star from users. We can get that data back. One thing to keep in mind, because it's a distributed system, you can't have an auto-incrementing column. That wouldn't make sense. So normally, if you need a unique key for something, you would use a user ID. But, I mean a UUID. But in general, you have to be careful, because partition key is how you have to look at this data. So, let's do this, let's start from users, where user ID equals this. Cool, it gives you back your guy. But the downside to all this, I want to say, let's start from users where age equals 30. You can't do it. There's no way to know what node would have a user with an age of 30. So for it to work, it would have to go to every single node in your cluster, look at every single column, and then you would lose the fact that this scales fast. So when designing your primary key, you have to be very careful that it's how you're going to search for these records. So in this case, I just did the UUID. Really with people, maybe you want to use your social or use something that you would actually be able to get back. It's kind of the complication of all this. You can also add multiple columns to the partition key. So I could have done, first name and last name as the partition key. And then that would say I could either search by just first name or first name and last name. So it's kind of, this goes back to when you design these tables, you have to think, how am I going to query these tables? And if you want to query in a column, it should probably be in the partition key. Questions about that? Those kind of should throw you guys off for a loop. What?
Is there an aggregation framework?
I think there's some aggregation stuff, but you still need to do it you need to be querying on your primary key too. So I forget the exact way that works, but it's not, right? And there's very basic, I can select count. There's very basic count for users, but to the count where the user ID is this. So that's equals. So you can count how many rows have that partition key. Because if you have a compound partition key, you could count just a part of it. But it's not, right? It's hard to throw a bunch of data in here and then say, okay, now I'm going to type up a fancy query and get this SQL report out. You have to plan, how am I going to look at this data, then use that to say, how am I going to store the data? Everything maybe you need to store each data twice, maybe you need to store it by last name as your partition key, and then you also need to store it by social security as your partition key. And then you have two ways to look at the data, but every time the data changes, you now have to update it in two places.
If you have multiple partition keys, how does that affect the balancing and distribution?
So it's smart, so it balances at kind of the tuple of both of them. So all people in the same first and second partition key will end up on the same node. Or you could have 3 or 4, you can have several. I don't know what the limit is, but you can reasonably have 3 or 4 partition keys. And then you can search from just the first part of the partition key, or the first and second, or the first, second, and third. You have to kind of start from the left side, kind of like using an index in a multi-column indexing database. You can't choose just to search on the rightmost part of the partition key, because again, it doesn't know what node it is. Other cool thing is this thing called tracing, and it basically says if your queries are going slow for some reason, you can turn it on, and you can see exactly how does it do the query. So I'm doing a select start from users, it's a little bit smaller, and it says, okay, I'm connected to the first node, And the first node is gonna say, okay, I did a consistency of 1, so he's gonna connect to this other node 2. He's gonna get some data, he's gonna read this data, he'll return that, and return it to the user. Then if you see if I do, in the terminal, you can set your consistency to kind of see, my consistency right now is 1. I could say my consistency is all. Now when I do the same query, you can see instead of just talking to one node, I went to node 1, node 2, and node 3. So you'll see read 1 cell, read 1 cell, read 1 cell. So you can see it read the data everywhere. And it should have done just a digest for 2 of the nodes. So it should only read the data from one node and just give a digest from the other 2. So that's interesting. And again, we go back to consistency. Back to consistency 1. And this consistency 1. So remember all 3 nodes are up. I'm going to stop node 3.
So in that query that you just ran there,
Yep.
how come the last line where it says custom page, it says 31.52, but before that it had gotten up to 0.54? See the line above that?
Yep. So it probably was able to, sometimes it's because it's able to complete a query before it's finished. This is the consistency of all, it probably didn't. My guess is this timestamp's probably not quite right. So it maybe could be above. I'd have to look at the, but this is, it's not, again, like these, yeah, you would expect the timestamp to be different there, especially because it's the same node, it should have the same time. But really, this whole thing took 9.8 milliseconds. It's probably fine. Like if something's going on, you'll see a very long time for one step, and it can kind of narrow down. I think that's kind of more the goal. I think sometimes we reuse timestamps or we do little tricks so we don't have to do the timestamps so much. I would just focus on the green numbers for most of the stuff. How long did it elapse and then how long did it stuff. But going back to my other story, I stopped node 3.
I stopped node 1.
I changed it to node 3.
Okay.
So I connected to node 1. So you see I have node 1 and 2 are up, node 3 is down. My consistency is 1. I'm going to turn this off. And I can still select from users because there is a node up that has the data. If I say consistency all, I'm going to no longer be able to get the data because one of those 3 nodes is down. It says cannot achieve level consistency all. Required replicas 3, alive replicas 2. So it's saying you can do this for you right now. You wanted it from all nodes. There's a node that's down. In node 3, if I start it back up, it'll rejoin the cluster. If there have been writes that I missed, anything like that, it'll catch back up. And then it works again. Magic. And then there's the demo at our conference is some guy had 3 Raspberry Pis set up. He was doing queries on it, whatever, and then he took a sledgehammer and smashed one of them. But the queries keep going because they don't care. If they feel if you only have consistency of 1, we don't care if one just exploded.
That's awesome.
I wish I had Raspberry Pis. Yep.
Can you add a column
With that one down?
and continue on? Is that on the fly?
Can
Like, so you have age, first name, last name, I don't know, like add middle name?
Yeah, there's other table stuff.
Okay.
What I can do is I can change the partition key.
Okay, so you can keep adding columns or do whatever.
You keep adding columns, and your columns, it could be a list column, which really just says you can jam all the data in you want.
Okay.
eBay, when they talk about it, they use, I think, 2,000 or 3,000 columns and some of their things. It's this is why it's a wide database. You have,
I see. The key matters, everything else doesn't.
yeah, everything else doesn't matter. It's, I mean, it's helpful to enforce the schema, like, users should probably have a first name and a last name. Just letting people, you know, you could treat this as one giant field and just jam things in there. That's kind of bad news down the road for you, but if you want to, you could. Yep.
How do you handle, I know earlier you were saying how it stores the original state of the database and then builds the database from there.
Yep.
How do you change what the original state of the database is? So suppose you had 100 million transactions, you wanted to combine those because those were all more than 8 months old, and you've got
Like
millions
a
more
summary
on top of
table or
that.
something? Or?
Yes.
Yeah, so then you would probably read those into your app, make a summary, write to the summary table, and then delete them from the original table.
Okay.
And then thered be tombstones, so maybe a couple days later they would actually get deleted.
Isn't that the process we call compaction?
Compaction, compaction is when you, it does other things, but yeah, one of the things it does is basically all the files that we're writing are kind of write-only, so we write files. At some point you have tombstones, you have other things, and you even have like 4 versions of the same data, right? Because if you change your age a bunch of times, you have all the other versions. Compaction gets rid of all that and says this is just the newest data.
It makes a new base.
Yeah, and there's compaction strategies which are complicated too, but there's like different ways you can do it. You can do it in kind of different steps. You can do it whatever, but it just kind of goes on in the background and cleans up stuff. Okay, any more questions on the demo? We got like one more slide and we're done. And then, okay, and then just the final plug is then what happens with DataStax Enterprise, which is a commercial offering. Everything you saw was Cassandra open source. DataStax Enterprise sits on top of that, and it does things like Lucene, Spark, Hadoop. It does, lets you build a Spark cluster or a Lucene cluster on top of Cassandra. So if you want to, Lucene something that lets you do search, build on top of Cassandra, and now you can have search with 1,000 nodes back in it. So it's just kind of the final piece of the puzzle is if you need something that scales, but is not just a database, you can look into Cassandra DataStax Enterprise for stuff built on top of that. There's a graph database, etc. Okay, that's all I got.